Today in the workshop, we're working with a precision temperature sensor. You'll see how to use the TMP117 and how it compares to other popular sensors. We'll also build a precision thermometer with an OLED display and a Wi-Fi interface. It's a hot and cold episode today, so welcome to the workshop. Well, hello and welcome to the workshop, and today we are going to be working with a temperature sensor, which is nothing new because we worked with a lot of them before, but this particular sensor, the TMP117 by Texas Instruments, is a particularly accurate temperature sensor. It's a precision sensor that is accurate down to 0.1 of a degree Celsius, and so if you really want to know what temperature things are, this is the type of sensor you want to use. Now today what we're going to do is we're going to look at this sensor. We're going to hook it up to a microcontroller and see how it works, of course. We're also going to compare it to a number of very common temperature sensors just to see how it fares against them. And then we're going to build a really neat project. We're going to build an ultra-accurate thermometer that has both an OLED display and works over Wi-Fi, so you can use it with your phone or your computer. It's based around an ESP32, and one of the neat things about the project is there's no soldering at all. It's just all snap things together and make it work. So a lot of interesting stuff to cover today, but first let's go and take a look at the TMP117 temperature sensor. The TMP117 is a precision temperature sensor. It's accurate to plus or minus 0.1 of a degree Celsius in a range of -20 to 50 degrees Celsius. It provides a 16-bit output and has a precision down to 0.0078 of a degree Celsius. This medical-grade sensor is NIST, or National Institute of Standards and Technology, traceable. The TMP117 uses an I2C interface, and you can select the I2C address. This is a low-power device that runs on 1.8 to 5.5 volts DC. The TMP117 is also programmable. You can program an interrupt to occur at a high and low temperature threshold. The device also has an onboard EEPROM. The TMP117 that we'll be using today is on a module from Adafruit. Other manufacturers also create modules for the TMP117. The pinout of the Adafruit module is as follows. The VIN pin is the input voltage, and this should be set to the same voltage you're using for logic, either 3.3 or 5 volts DC. GND is of course the ground pin. The SCL pin is the I2C clock. The SDA pin, the I2C data. And the INT pin is an active low interrupt output that can be programmed for either a high or low temperature threshold. Finally, the ADDR pin allows you to set the I2C address of the TMP117. So now let's go and take a look at the TMP117 module. And here it is, the Adafruit TMP117 precision temperature sensor. And I've got mine mounted onto a solderless breadboard, which meant I had to solder some pins onto it. It comes with the pins, but they are not soldered, and you don't necessarily need them. You'll note that on either side of the sensor, on the left and right side, there is a Qwiic connector, and you can use either of these connections to connect it to a microcontroller that supports Qwiic connections. That's an I2C bus at 3.3 volts usually, although it can also be 5 volts, and this sensor will work with both of those. Now, on the center, you will see the sensor module itself. It's right in the very center of it, and you'll notice if you look that the board is cut out around that, and that's pretty typical for Adafruit environmental sensors. They cut the printed circuit board around it to allow the air to flow better. One thing you'll want to make note of is that because this is such a sensitive temperature sensor, it'll also pick up heat from any of the other components that you're wiring it with. So if you're wiring it with a microcontroller, for example, the heat from the microcontroller could affect it. So you'll have to make sure that you mount it where it's not going to be affected too much by the other components. But otherwise, it's a very easy component to make use of, and we're going to do exactly that right now. Now, I should mention that throughout today's video, we are going to be taking temperature measurements using the Celsius scale. The Celsius scale is, of course, the most popular temperature scale in the world, being used by 95% of the world's population. However, if you prefer Fahrenheit, it is very easy to convert Celsius into Fahrenheit. You can do that within code, and when we build our project near the end of the video, I'll show you how you can set the output to Fahrenheit if you prefer that over Celsius. At any rate, now that we know more about the TMP117, it's time to hook it up and take a look at it, so let's do exactly that. Now for our experiment, we will of course need the TMP117 module, and we'll need a microcontroller, and I'm using our old friend the Arduino Xiao ESP32S3. You could pretty well use any microcontroller for this experiment though. We'll begin by connecting the V-in pin on the TMP117 to the 3.3 volt output on the Arduino Xiao. The ground pin on the sensor will of course be connected to the ground pin on the microcontroller. The SCL pin will be connected to pin D5 on the Arduino Xiao, and the SDA pin will be connected to pin D4 on the Xiao. And that's it for the wiring. Now let's go and take a look at some code we can use with our TMP117 precision temperature sensor. Now, in order to use the TMP117 on the Adafruit module, you're going to need to install a library from Adafruit. So go into your library manager and just type in TMP117 and install the Adafruit TMP117 library. When you do, you're going to get prompted to install another bunch of libraries, which will be installed for you. They're related libraries. Chances are you probably have a few of them, but just let it go ahead and install all the libraries it needs. And this is a basic test sketch that comes with the library. You'll find it in your example sketches. And you can see that it's a pretty simple one. It includes the wire library for I2C, as well as the Adafruit TMP117 library and the Adafruit Universal Sensor library. We start off by creating an object for the TMP117, and we go into our setup where we set up the serial monitor, and then we initialize that object over here. So that's pretty simple. Then we go into the loop, and what we do is we create an empty event called temp, and then we populate that event over here with a get event, and we get the temperature. So we fill it with the temperature, and then we go and we print that out to the serial monitor. So temp.temperature will print out our temperature to the serial monitor. We add an extra line in at the bottom, a blank line, delay for a second, and go back and do it again. So it's a pretty simple demonstration. Let's load it up to the Arduino Xiao and watch it work. And so here's the TMP117 precision temperature sensor hooked up to my Arduino Xiao on a small solderless breadboard. And if we take a look at the serial monitor, you can see that every second it's displaying the temperature down to 2 decimal points. It seems pretty accurate. The only thing I can judge it against is a thermometer I already have here in the workshop, and it's very close. And I'm sure this temperature sensor is more accurate than my workshop thermometer. So at any rate, it's a very basic demonstration, but it does show you how simple it is to use the TMP117 precision temperature sensor. Now, being a precision temperature sensor, the TMP117 is naturally a bit more expensive than the other sensors that we're used to using to measure temperature. And you might wonder if it's actually worth it. Well, it really depends on how precision the temperature reading you need for your application. So what we're going to do right now is take out some of the more common temperature sensors, ones that you've probably used before. We're going to hook them all together, and we're going to compare them to the TMP117 and see how their readings are. Now here are the additional temperature sensors that we're going to be comparing to the TMP117. We have the DHT11 and the DHT22, the MCP9808, the AHT20, the AM2320, the LM35, and the TMP36. The DHT11 is a digital sensor. This is an older device with a range of 0 to 50 degrees Celsius and an accuracy of plus or minus 2 degrees Celsius. The DHT22 is an upgraded DHT11. It's also digital and has a range of negative 40 to 80 degrees Celsius with an accuracy of plus or minus 0.5 degrees Celsius. The MCP9808 is a digital I2C temperature sensor. It has a range of -40 to 125 degrees Celsius and an accuracy of plus or minus 0.25 of a degree Celsius. The AHT20 is also a digital I2C device. It's a very common device and has a range of -40 to 85 degrees Celsius with an accuracy of plus or minus 0.3 of a degree. The AM2320 looks a lot like a DHT22, but this is actually an I2C device. It has a range of -40 to 80 degrees Celsius and an accuracy of plus or minus 0.5 degrees Celsius, the same as the DHT22. The LM35 is an analog temperature sensor with a range of -55 to positive 150 degrees Celsius. It has an accuracy of plus or minus 0.5 of a degree. And the TMP36 is also a popular analog temperature sensor. It has a range of -40 to 125 degrees Celsius with an accuracy of plus or minus 2 degrees Celsius. So let's see how these all compare to the TMP117. And here's our multi-sensor demo. Now, I'm not going to give you a wiring diagram because I strongly doubt you're going to want to wire one of these up yourself, but it can be easily explained. Now, you can see it's based upon an Arduino Uno R4 Wi-Fi board, and I chose this board because it has a 5-volt output instead of 3.3, and some of my older sensors work better with 5 volts. However, most of these will work with either 5 or 3.3. I'm also making use of the Qwiic connector on it. You can see the Qwiic connector at the top of the Uno board over here, and it connects to 2 of my sensors over here. These are on the breadboard, but their pins are actually connected through the Qwiic connector, and they're daisy chained. And this is the TMP117 itself, and this is the AHT20 over here. So they both use the I2C Qwiic Connect. The MCP9808 is over here, and that uses the other I2C bus, the one that's on A4 and A5 of the Uno. Right next to it, the AM2320, also I2C. Next to that is the DHT22, which looks a lot like the AMT2320, and actually a DHT22 can also be called an AM2302, so it's almost the same part number, but this is connected to one of the digital inputs, and the other sensor next to it is the DHT11, the very old sensor, also connected to a digital input. That's these back over here. And finally, in the front, I've got my 2 analog sensors, and they're connected to A0 and A1, my analog inputs. And they're actually one of the reasons I needed 5 volts, because they're calibrated for 5 volts and not 3.3. And so basically, it's been running for a little while to stabilize. The temperature sensors, as you can see, are quite close together. I also threw a filter capacitor onto the board just in case the power supply had some issues with all these devices. So now let's go and take a look at the serial monitor. I've written some code to drive this. Again, I'm not going to go over it with you because I doubt you're going to use it. But if you'd like the code, I'll include it with the downloads for this episode on the dronebotworkshop.com website, so you can always grab the code. So let's go and take a look at the serial monitor and see how our sensors are faring. And here are the output of my sensors on my serial monitor, and I have so many sensors that I'm going to have to scroll to the side to look at them. But let's just take a quick look. Now, the reference over here is a TMP117, and as I said, it's been running for a while, so it seems to have stabilized pretty nicely. And the next to it is the DHT11, which is the oldest sensor over here, and you'll notice that there's nothing after the decimal point. That's because the DHT11 only resolves down to a resolution of 1 degree Celsius. And you can see it's actually not too far off. So this old temperature sensor actually works pretty well. The DHT22 is the more modern version of the DHT11, and it's very close. If you look at the readings we're getting over here, they're not off at all. It only resolves, by the way, down to 1 decimal point as well. So you'll always see a 0 as a second digit over here. The MCP9808, a very nice I2C temperature sensor with a lot of addresses. So if you need a bunch of them, you can connect them to the same I2C bus. It's reading pretty close, maybe about half a degree or so off from the TMP117. The AHT20 over here is very impressive. It's within a fraction of a degree from the TMP117, so that's actually very impressive. That's a very common I2C sensor, and it's very inexpensive as well, so this is probably a good choice if you're looking for an all-around temperature sensor and don't want to pay the premium price of the TMP117. The AHT20 also measures humidity, by the way. The AM2320 is the I2C version of the DHT22, and now we had to scroll for that, so we can see that it's, it's pretty close. 25.36 and yeah, 25.3 is very, very close. The LM35, now this is one that's all over the map, and I'm wondering if I may have a defective sensor. Now I tried another one because I had a couple in my parts store. They both gave me about the same responses. They should be good sensors. I purchased them from Pimeroni, so they shouldn't be secondhand ones like the ones you get on Amazon or eBay, yet it's dancing all over the place, so it's really hard to get a good reading on that. It's a shame because that's a good temperature sensor to use if you need a wide range of temperatures, but from my experience here, it's not that accurate. Now, mind you, it's an analog sensor, and that could have something to do with noise on my analog line. I did add that filter capacitor, but it didn't seem to make a difference. And finally, on the end, the TMP36, a very inexpensive analog sensor. It's actually a little more stable, although as you can see, it's reading quite a few degrees above the actual temperature, which I'm going to assume is what the TMP117 is measuring. Now, again, these are analog sensors. They're dependent upon the supply voltage, and that supply voltage is powering a lot of sensors. Maybe it's down a bit. If you use the analog reference pin on the Uno, you could apply a reference voltage to that and use that as well for the sensors. You may get a more accurate reading. It seems to be pretty stable, but again, it's a few degrees hotter than I would have expected it. But all in all, most of these temperature sensors give pretty well the same readings. So, of course, if you need a precision device, you want the TMP117, but something like the AHT20 would work great, and it's a lot less expensive. So you can use this to kind of make your mind up when you're choosing your next temperature sensor. So now let's use our TMP117 sensor in a project, and the obvious project for it is a precision thermometer. We're going to hook this up with an ESP32 and an OLED so that we can have a thermometer that displays on the OLED, and that also works with the ESP32's Wi-Fi so that you can use your phone or your computer to take a look at the sensor as well. What's interesting about this project is that if you use the components that I'm using, you won't have to worry about any soldering or anything. Everything I'm using uses a Qwiic connector, and so we're literally just going to plug everything together, program it, and watch it work. Of course, you could use different components if you want, and if so, these are just I2C devices, very easy to connect up and wire, and you can build essentially the same thing. The components I'm using also have an additional advantage in that they support charging a li-poly battery, so we can connect the battery to this and have it charged through the USB-C and have a really neat device that we can build in a few minutes and that can sense temperature very accurately. So let's go take a look at how we build this. I'm going to be building our project around a really cool little ESP32 board from Sparkfun, the Sparkfun Qwiic ESP32C6 Pocket Development Board. For a board with such a long name, it's actually a very tiny little board, and it has some great features. First of all, it has an ESP32C6, which means it's Wi-Fi 6 compatible. It also has a quick connection for easy connection for I2C, and that's what we're going to be using today. Another feature I'm going to make use of is the fact that it has a connection for a li-poly battery, and that battery is charged out of the USB-C cable that's also used for communication. So it's a really great board to build a project around. We'll be using this board with our TMP117 precision temperature sensor and with an OLED display. I'm using a 128 by 32 Qwiic OLED display, also from Sparkfun, but you could use any Qwiic Connect OLED. Of course, you could also use a standard ESP32 and OLED display and connect everything up through the I2C bus. In our case, the connections are quite easy. We'll connect the Qwiic cable from the ESP32C6 to the temperature sensor, and from the temperature sensor, we'll connect another Qwiic cable over to the OLED, and that completes the wiring. Now let's go and take a look at some code we can use to build our precision Wi-Fi thermometer. And here's the code that we're going to be using with our ESP32 Precision Thermometer. And there's a fair bit of code over here, but that's because, of course, we're using a web server. Otherwise, it's fairly simple to understand. We're going to start off by including the required libraries, and you should look at this to make certain you have them all. The wire and Wi-Fi and web server ones are already included in your IDE. You don't need to worry about those. Adafruit GFX, you may have that installed if you've ever used any Adafruit graphics products, but if not, you'll need that. This is the SSD 1306, and that's for the OLED. You'll have to install that. And you probably already have the TMP117 installed, but if you don't, you'll need to install that as well. Now we'll configure the OLED display, and then we'll configure the Wi-Fi point access credentials. And you could change this if you want. Right now, we're calling the Wi-Fi point ESP32 temperature, so that's what you're going to be looking for when you connect to Wi-Fi. And here is the password for it, temp12345. And of course, you can change either of those if you wish. Now we're going to create the objects for the web server and for the OLED display and for the TMP117. We'll set up some variables for temperature, one for Celsius, and we're also going to display Fahrenheit for you Fahrenheit fans here, so that's over here. And then we'll go into our setup here. Setup is fairly simple. We'll start the serial monitor. We'll initialize I2C. We'll initialize the OLED display down here. And then we'll clear that OLED display and just print initializing on it. We'll initialize the TMP117 temperature sensor. If we get an error, we're going to print that to the serial monitor and the display. But assuming we don't, we're going to find that and go and set up our Wi-Fi access point with the SSID and password that we specified earlier. And we'll get the IP address or the access point. And over here, we set the routes in the web server. There's two to look at. This one over here, handle temperature, and this one over here, handle route, are both going to be used. Then we'll put a startup message onto our OLED display, and we will leave the setup. Now we can go into the loop, and in the loop we'll get the server to handle all the client requests, so we'll start that off. We'll read the temperature from the TMP117, and then we'll get the temperature, which is automatically in Celsius, and we'll convert that to Fahrenheit down over here. So that's how you convert Celsius to Fahrenheit. And then we'll print all that stuff to the serial monitor. We'll clear our display, and then we'll print on the main OLED display. Now the way I've got it, I'm printing Celsius in large text and Fahrenheit in small text. But if you would prefer Fahrenheit, you can reverse this. So make this the temp F over here and the temp C down here, and you'll essentially reverse that. You'll also want to, of course, change the C and the F symbol here. Okay, and then we'll update our display, and we'll delay another second before we go and do it again. So we'll take a reading every second. Now, handle route, which we saw earlier, is how we actually construct the web page. So there's a lot of HTML, and there's a lot of CSS over here. And you can, of course, change the CSS if you don't like the looks of the page. I kind of went with a blue and white motif, but you can, of course, adjust this. I'd suggest you load it up first and then make your modifications later. One thing I did want to show you over here is this. It's pretty cool when we get to the header. There we go. We get to the header and the button over here. We've got these little emojis. Now, how did we do that? These are called Unicode emojis. You can Google and get these and just literally paste them into your code. You can also put a text number inside here, some text with a number behind it that indicates a Unicode emoji. And if you want a little more information about that, the article that accompanies this video on the dronebotworkshop.com website tells you a bit more about how to do this. At any rate, we finish off the HTML over here, and we send it out. And over here's handle temperature, how we continually update our temperature. And so we just basically get the Celsius and the Fahrenheit string. Okay, so that's basically the code. It's, like I said, a lot of code, but not that difficult to understand. Let's load it up to our ESP32 and look at our precision Wi-Fi thermometer. And here we have our completed Wi-Fi Precision Thermometer, and as you can see, it's a pretty simple hookup thanks to the Qwiic connections. I've also connected a li-poly battery to it, and that's what's powering it right now. So it's not even connected to the computer, and the OLED display, as you can easily see, is displaying the temperature in both Celsius and in Fahrenheit. Now, in order to display this on the web, we need to connect to the access point that was created by this, give it its password, and then once we're there, we take make a web browser, we go to 192.168.4.1, and we will get this, the temperature monitor's web display. And as you can see, it shows basically the same data, the temperature in Celsius and in Fahrenheit. It has a refresh button on it, and it's been styled so it'll work with just about anything, with a phone, with a computer, which you're seeing right now, or with a tablet. And so it's a pretty simple project to build thanks to the Qwiic connectors, and it works very well. And so if you need a precision Wi-Fi thermometer, this is the way to go. And remember, with the ESP32C6, it's also Wi-Fi 6 compatible. So if you're looking to build an IoT device, this is an excellent way to do it. And so that about wraps up our look at the TMP117 precision temperature sensor. I hope you enjoyed the video, and I hope that it's opened up your eyes to this new sensor that you can use in a number of your projects. Now, if you want some more information about the TMP117, or if you'd like to grab the code that I used today, you'll find all of that on the article that accompanies this video on the dronebotworkshop.com website, and there is a link below the video to that article. While you are on the website, if you haven't yet, please consider signing up for my newsletter. No, it's not a sales letter, just my way of letting you know what's going on here in the workshop and occasionally giving you previews of my videos. And the newsletter is free to sign up for. All I need is your email address. If you're also willing to give me your first name and make up some kind of crazy username, you can join the DroneBot Workshop forums, where you can discuss electronics and programming with a number of like-minded individuals, help them out with their projects, and they can help you out with yours. And the forum, of course, is free to sign up for. And while you're in that signing up mood, and if you haven't yet, why not subscribe to the YouTube channel? I make videos about electronics and microcontrollers. If you like this video, you'll probably like my other ones. Subscribing, of course, is very easy. All you need to do is click on that red subscribe button and also click on the bell notification. As long as you've enabled notifications, you'll get notified every time that I make a new video. So until we meet the next time, please take care of yourself, stay safe out there, and I'll see you soon here in the DroneBot Workshop. Goodbye for now.